for that. And there's definitely, I think you cover two different aspects. One is that there are processes that are coupled, and one is that we sometimes separate our understanding of the world in different pieces of software, different models, and then we try to couple those. So I'm not going to talk about the first one. I'm going to ask about the second one. And it seemed to me that what I would like to learn from the climate modelers' experience is what from an outsider of observation I have is that we talk about building modular frameworks of integrated models, but in effect often nobody is replacing any of the subcomponents with anything else. We end up with one integrated assessment model, and then we build a completely new one in another part of the world, another group of scientists, if you like. Whereas in the climate models that I've seen, there are many common components, but it's often a single piece of Fortran that they copy and pasted, pieces of code. So it was, if you like, an integrated model, but actually at the level of Fortran pieces. And obviously that works very well, but it's not modular. If we actually want to solve the problem of model discrepancy, which I think this is why we want to have a modular framework. Do you have any good examples of where, maybe in the climate world, people actually explored an easy way of combining many different combinations of models?
Who wants to take that first? Okay, I would say something like the land surface models fall into the middle of this. So it is true that there's common code between some of the climate models, and so in a way that means that people focus on that. Depending on which model you put it in, you learn something about. As you say, you go to the other extreme, all the people around the world create their own IAMs, they just bolt together whatever the local modelling bit is. To answer that specific question of could you then go back and pick apart the different bits, I think the land surface models perhaps fall into that. So the land surface model like Jules, I would say, gets picked up by a lot of different groups around the world. So you do get some feedback on how well your model's performing. I think there's a concern about the fact that there's common code between models, and I think for the emergent constraint thing that can be an issue because maybe a few of the points aren't completely independent.
I was going to pick up on that because I guess what do we want in the end? Do we want all one model that we think is the best? But I think actually because we don't really know, like I was saying, we don't know the best equations actually to represent certain parts of the Earth system, that it's worthwhile to have these different models that are doing different things. But you're absolutely right. In climate modeling, there's not a modular approach. It's copy and pasting, or you go to a conference and you hear something great and you plug that part into your model. I think that's something that could be improved.
So just a very quick point from my perspective. So I think the difference potentially between the communities that are trying to link different land sector models together and the climate communities is they're very large multi-institutional groups who are trying to put together models that have been historically developed with completely different coding environments on completely different platforms, and the resources are not available to completely recode all those models in a common language. So they're almost trying to just find another way of doing it, and that's why I was quite hopeful when Gordon Blair, who is in the audience at the back, said that sometime in the future we need something that is more open, allows modular coupling, provides some of the building blocks that we can work with, because at the minute we're all trying to do it independently and often not in a very good way. And as soon as the funding ends, we're stuck with that system. You need repeat funding then to start replacing and improving as we go on. So I think it's just where we're at the minute, and I'm hoping as we go forwards there are better solutions. Right, hang on, let me just check, because I think there was Marcel, Peter and Lex.
Thank you for two fantastic talks. I just have a question about the rasterized view of the world that maybe comes from climate modeling, where we have to make all these boxes over which things happen. do you have any idea about any possible constraints that worldview gives towards coupling with Lagrangian models, models where particles move, individual-based models, agent-based models? Are there any possibilities that we are losing because we are so focused on the rasterized view?
Which one do you want that?
Well, certainly the Lagrangian approach, where you follow things through, even though it's, as you say, split into particular shapes, it's all on. GCMs all tend to be on a regular XY. All the GCMs tend to be on a regular XYZ grid, but there are sort of pieces of code that they can let loose to follow how things move around in the climate model. So one very obvious example is that there is a version of the Met Office model called NAME, I think, which is used to follow around pollutants. And the name, don't formally quote me on this, but I think stands for the Nuclear Accident Modelling Environment. And so this was the idea that if something happened in the world, your Lagrangian, you could follow around where the pollutant is. Of course, it's used for other things, and it was used when the volcanoes went off in Iceland. So it is possible to move things around in these models. I mean, in effect, you have to save the advection terms, right? So you can rebuild it offline, if that's what you're asking. Yeah, but if the agent model isn't there in the first place, so it's not represented, I don't know what you would do.
Yeah, I mean, do you kind of mean if you wanted to have your climate model, but then have things happening on the land surface that are responding not in like a grid, where you've got migration or river flows or
Yeah, we have had so many talks about biodiversity and dispersal and such. I was just wondering whether there are any constraints that we have learned to live with because of this dominance of the climate modeling, rasterized thinking.
So isn't hydrojoules doing this? Isn't it going to have a sort of grid based on catchments rather than regular?
Yeah, that's possible.
I think so.
And
That's possible, but could you just make the coupling a bit more complicated? But it might well be worth doing that to retain a grid that makes more sense for the subcomponents. Seems like we're getting there on that.
So
yes.
Peter, you had a question.
I did, sorry. It was just, thank you for the talk, it's great. So Anna, you showed this increase in, this cascade of uncertainty. And Chris, you showed this importance of coupling and how you get emergent properties, like with the classical Lorentz model, for example, where you just get chaos you wouldn't get if it wasn't coupled. One of the things I think we miss sometimes, because we get obsessed with this whole issue of feedbacks being the source of uncertainty, is that feedbacks also often help with the cascade of uncertainty, because basically you get to some of those points on your bottom of your cascade, and they're not consistent with what you said initially. And when you couple it together, and this is also true at a very large scale, say the RCP 8.5, it's driven by economic growth that frankly is going to be impossible if we have the climate change of RCP 8.5. Because we decouple them, we actually end up with a more uncertain world, less rich world, so you don't get oscillations and things like that, but what you end up with is this view that you could have RCP 8.5 emissions and the climate change that produced it, and still have the economic growth that was implied by RCP 8.5. So I guess what I'm saying is that, and this is again is a classic politician trick, do you agree that sometimes coupling models reduces uncertainty?
But wouldn't it be great if we could get to a point where these integrated assessment models are actually working with a climate model that also has the impacts of the climate change? So you wouldn't get to that point where RCP 8.5 climate, but agriculture's booming because it's using an annual average something, and not representing small scale climate change effects. And,
Okay, Lex, I think you're next.
Yeah, it was just something that Chris said that I thought about Net CDF. It's a very well developed community, lots and lots of standards, especially for data. And in previous lives, I've worked a lot with kind of those kinds of groups in terms of the metadata, and I just wondered whether there are any kind of metadata standards for models climate models that could be used to at least start helping understand some of the perhaps different assumptions embedded in the model. I mean, in the end, for some of the stuff I was talking about, like where data have different ontologies, we'd say standards are useless. But you know, but I wondered whether there are kind of initiatives like that within the community. And there was just a follow-on point to Marcel's there. We're in terms of different resolutions. We're in kind of GIS, if you want, spatial analysis now. Quite happy to work with data with objects that represent completely different areas all the time, whether it's points or rasters, hexagons, cartograms, and where the area is defined by some homogeneity in some dimension that we're interested in. So we change scales depending if we stay within a homogeneity scale, but that has different size and area implications for different places.
Well, I would say that the NetCDF format has revolutionised from the climate change perspective, and I think because it's a relatively easy thing to use, I think climate data is being picked up by people who would otherwise regard the science as quite impenetrable. You know, they quite quickly get to grips with it. Now, if there was some common, similar format that all of you that develop IAMs or the components, I mean, you could even get the two to talk to each other. I feel that's something, Paul, I'd like to ask you actually, but bounce that to you if you think that all the things we've been talking about, we could have some common language. So what was the thing you actually said you used? Was that something that we could use?
Well, no, I was involved in all of these metadata standards and spatial data about 15 years ago, and fundamentally trying to kind of how do you match things together that have different assumptions, constructs, or whatever. And essentially, you know, what we worked out was that standards were useless, but they were very good for data producers. Do you know what I mean? They told their bosses they'd done a good job. And what I just wondered whether there were. But I know that the NetCDF community, and we had Brian Lawrence, is it? I can't remember. He was a real kind of no, standards is the way forward, and it worked in that community because everyone in the community was talking about the same thing. And I just wondered whether there was a parallel here, where with climate modelling, when you're trying to couple, is there a way you're all kind of talking about the same thing? So you've got shared vocabulary, ontology, whatever you want to call it. Where there's opportunities. I don't know whether it would make more work than just kind of like, you know what, I know what's going on between these two models, I'll just wang it together.
Yeah, so I could repeat the quote that Ian Holman gave in the opening workshop here, that so in our integrated modelling platforms we chose not to follow any standards. Just partly because it's the time it takes to do that. You're almost right at the end of the project and you've still not started to even try and link your models. But we did go through quite a strict process of huge amounts of communication and trying to capture that in sets of we call data dictionaries, which are in a way a bit like trying to get your semantics sorted. But we did it in our own way, and I think there is an awful lot of learning from these projects that can go forwards. And again, it's finding that balance between what works and what doesn't.
Where we ended up, so I'll just finish, I know there's other questions. Where we ended up was actually metadata standards were only good for bosses, not for the users. And what really helped was all the documentation around the decisions that were made at various stages. And that included minutes from every meeting, papers that had been published, the whole shebang. That was all metadata.
Right, okay. Is this directly related? So do that and then we'll go to Mark, okay.
So, in other communities, such as systems biology, they have a thing called SBML, which is an XML description for their models. So their models don't exist as code. Their models exist as SBML files, and then you can get a piece of code that will write that as in Fortran, or it'll write it in Python, or it'll write it in whatever language you like. We're probably too late in landscapes and climate to actually do that, because I think you have to start a long time ago. But that sort of system, which documents models in a very formal way, is a way forward, and I think probably the self-writing climate model is probably not going to happen. But a more formal structure for how we document models would be very useful and would help with coupling, because you can actually see what assumptions were made, what inputs really are, because sometimes things have the same name but they aren't the same thing.
Exactly.
and that's a suggestion. I mean, it's not going to be cheap.
No, exactly. I think it takes time and resources to do those things.
I wonder if there's a recommendation then, thinking about tomorrow, that actually, I wonder if there's a recommendation that there is some money set aside for this as a future exercise, in much the same way as the IPCC must have at some point said, we're going to set aside money for people to develop this software interface. It's very easy to get obsessed by these things, but I do think it's important, because the thing that's so great about NetCDF is not so much the beauty of the files, and you're looking at something that's easy to work with. It's indisputable what you're actually looking at, and I think that reduces the risk of errors appearing in peer-reviewed papers.
The same thing for code.
Yes.
Do you want to say anything? Not coming.
Okay, yeah, I agree.
Yeah, okay. So we've got Mark, and then we've got the gentleman behind him.
Thank you. I'm a big fan of coupling, I have to say, of model coupling. And as someone that comes from a Bayesian background, I see model coupling as something that sits very well within that paradigm. So I try and do it wherever possible. But I haven't heard this morning anything about the Bayesian way. And the reason I think the Bayesian approach is so valid in this situation is because the Bayesian approach, the paradigm, doesn't distinguish between something like a model output and a parameter. To the Bayesian view, it's all the same thing. And therefore you're able to not only share and to couple model outputs, but actually parameters, and importantly, uncertainty distributions. So firstly, is that something that you are aware of as a possibility? And secondly, just to follow up something that Peter said, the question that you posed, can model coupling reduce uncertainty? I think it probably can if, for example, you're dealing with outputs that are correlated. Because if by coupling you then accounts for the correlation between outputs that you might be linking between models, then that ought to reduce uncertainty. Now, is that something?
I think, based on Peter's view, that the feedbacks may actually reduce the uncertainty. This is something we can capitalise on to give more profound projections into the future. How do you characterise that? How do you characterise that you have two models with this uncertainty and they reduce down? Obviously, you can plot it up in a simple way, but if that statistical way was a way of formalising that, I think that would be superb.
Yeah, and then you're talking about Bayesian so are you meaning emulators by that, or is it?
I mean anything.
Yeah.
It could be an emulator, but it could actually be the output of a model.
Okay, yeah. So that, I guess as far as emulators, we've been thinking about that, but from climate community, I guess it's kind of new methods that we're hoping to explore more. Yeah.
So just very quickly, seeing as so that exact idea almost has gone in as a EOI to the large maths call on actually can Bayesian approaches help us with model coupling between agent-based models and more the sort of the global trade type models to overcome some of those issues.
Great, so it's on the board.
It's not actually on the board. It was the one that came after. So many others. So hang on, gentlemen.
Yeah, just to come back to the point about using kind of generalized markup languages to make it easier to write models. I mean, I have quite a lot of experience with these markup languages in other contexts, and they have a lot of really big problems in my experience. I mean, the primary one is the two-language problem, that the people writing the models are now constrained by whatever was implemented in the markup language, unless they speak both languages. They speak the markup language and the underlying language that the model was written. But the other one is just that they're fantastic when you have a simple problem and you don't really care how fast the code is going to run, because you write this really nice simple description of your model and bang, it's done, and it's all implemented. But my experience is that every time I start writing a complex model, they're never fast enough, and then I have to write the whole thing from scratch anyway. Unfortunately, I wish it were not true.
Yeah. Do you want to?
All I was going to say is, if it was possible to use that language, but then we had resource to translate that into something that bit compares, it's verifiable as it bit compares, it's written in Fortran, which of course is a very fast assembly type language, you can have the best of both worlds. It just takes time, right? So you have to have someone who, as you say, knows both, but was also prepared to confirm that things bit compare. So this lump of Fortran follows precisely this metafile way of describing the model.
Yeah, but that might be significantly harder than, I mean, that would be great. That would be great.
Yeah, I mean, maybe a related issue is like at the, so when it's time to run the models for CMIP, the coupled model intercomparison project, which goes into the IPCC reports, all the climate model output has to be, there's a format, common format that they follow in the NetCDF files and for all the outputs, and it takes like months, I think, to make sure your outputs are in the correct units and you've added things up correctly. So yeah, I think there's a balance between making things more clear to other users outside of your discipline, but not spending too much time doing it so you don't get other things done, like you said in your projects. So yeah.
So,
Oh, sorry, go ahead.
I just wanted to follow on though. A couple of points that have come up is it's so easy, I think, when you're doing a piece of research that you really just want the staff time for the research, and it's very easy not to stand out for investment in people who will do a lot of the software engineering. And I think that there's a time and a place where that's really important, and I hope if when the great and the good turn up tomorrow, if they turn up with a big check, we can add in a request for precisely precisely some of this. Yeah.
Zero on it, Chris.
So apologies.
But from that point of view, I mean, I think that we need to think about languages not like Fortran, that are both clear and easy to understand at the point of writing, and fast, like say Julia.
So James, did you have your hand up? Is it still relevant?
Yeah, it's a digression from discussion so far, but I thought it was relevant to some of the points made. In data world, there's a lot of emphasis on open access, people collecting data, they're publicly funded, making it available. In model world, some people are very open with their models, and others are like, you can only work on this model if you fund us. I was just wondering what the panel's thought on open access to models, how that might work, and actually it would be helpful for coupling.
Yeah, well, yeah, I think open access is becoming increasingly important, as it should be. The difficulty with the complex models is you also need access, just having the model code actually isn't enough, because if you had the code for a climate model and you tried to run it on your laptop or whatever, you'd be sitting there for a while. So I guess, but still having the access. What's the word I'm thinking of? Not open access. Transparency. Thank you. That's a good one. Yeah, transparency of what's going on in the models. Maybe even if it's not the code itself, but what the assumptions are. But yeah, do you have something to add?
Only really, I think perhaps one of the best pieces of advice that was ever given to me was whatever you do, tell everyone about it, because actually your models don't just disappear or find it's taken up by someone else. More often than not, people always feel a bit nervous about using someone else's model and will quite often come back, and when they come back, they'll often come back with new ideas or pull you into their grant, and that was advice you gave me, Peter, and I think it's great advice. So I think being open with models doesn't, there's always going to be someone that runs away and it's suddenly their model or something, but it's in general, I think the more open you are, actually the more comes back and the more your product is developed.
Okay.
I seem to recall, correct me if I'm wrong, that the ECMWF, the NWP model, there is a stripped down kind of academic version available. So that would mean, so you can use it on your laptop. Well, I'm not sure your laptop, but you can use it on something much smaller, and that makes the model already much more accessible. So one can do that, even when the model is big. Make a stripped down academic version or Aqua Planet version or whatever.
Yeah, and I think these kinds of things are useful not just for, that's useful as we're thinking about how to translate these models into things that are useful for policymakers as well. So is there some, stripped down web-based version where you have your options that you put in and you try to see what they do? But as we've been saying, that's a whole research program in itself. Do you want to add anything?
No, I just think if we had a good web interface that policymakers can use, I think, that'd be great.
Okay, quick one over here.
I'm quite interested in the psychology of model coupling, I think. So I was interested in your picture where you had, you had a economic model, effectively, the NEVO model, and although I'm not picking on you really, and then the Jules model. And when we talk about model coupling, do we talk about coupling the models that we can access? Because you had a set of inputs which were climate and land use, and actually they're models. And there's a inherent, I suppose, feedback when you start to alter the vegetation, it will impact the climate, etc. But that never changes. They're kind of treated as the same input. So what is your psychological approach to model coupling in a way? How do you think about it?
I mean, yeah, I guess everything would be a big loop if you were really being honest about it, because it all loops back and affects itself.
We don't think about
Yeah, so you have to choose your starting point somewhere, which is what, yeah, so what do we do?
Yeah, I mean, I think it's also, there's no one model of the whole system, so it depends on what you're trying to answer as. So sometimes you might not even need to couple to answer a particular decision or what the context of that decision is, and other times you might only need to link two models quite simply, and other times you might actually have 10 models together. So I think it's actually, I mean, for us in science, we're usually responding to a call, and that call you have to then work out what is the question or the decision you're trying to answer it, and then you start to build your consortium around it, and then you are limited, as you know, by available models and often who you know to collaborate with in those consortia. So that sometimes leads to really new, interesting collaborations, but also can help build on existing ones, and there is, I guess, a whole psychology behind that, and I think that's partly linked to the question that Guy started us off with, is if you do start to build these bigger and bigger models, actually, unless there's some open system that allow you to almost plug and play, which is maybe the holy grail of take one model off and put yours in, but you've still got to make sure all the connections work, then you can start to look at actually what are some of the uncertainties from representing part of the systems in different ways. But I think we're still quite a long way from actually managing to get to an environment like that. So, Peter, you're going to have the last
Thank you.
word.
So just on that, because it did resonate with something I wanted to say. I mean, we have been going for this holy grail in climate science, where it is potentially much easier than the landscape problem. Everything's written in Fortran, they should better talk to each other, and we've not done it, right? So there are half attempts to do it, like with the Oasis coupler, which is just fairly crude things. So my question, I suppose, and this might be something we answer in the breakout groups, is it time to give up on that particular way of doing it? Because basically this idea of having a general socket to put in your code, it's such an overhead that no one does it. There is a better way to, and I'm looking at Danny here, who's not concentrating, it's a better way to do it. It's a better way to do structural uncertainty, to just emulate everything. Is that the way we might do it instead? So statistical emulation submodels, no pressure, and then basically you span it through the statistical emulation. You don't try and do this thing of saying I take a bit of deterministic code and plug and play and do all the possible structures. You do it like that.
So my quick answer to that, it was in Marcel's talk yesterday. They had that nice diagram from Chandler et al. and showed how the differences between models give you some handle on an uncertainty that's coming from the models, but structural uncertainty has this other piece which we suspect might be a lot bigger. And a lot of effort in that direction might lead us to feel like we've done the job when.
So the problem is you don't think the models span the range enough.
Yeah, I mean maybe they do in terms of temperature, but not in ways that we get there or in the different things.
Statisticians always want the world to be even more uncertain.
I think there's another point, is whether, we've started looking at this for networks, that if you emulate different bits, do you get emergent properties when you stick them together? And I think we don't know.
That's when you need a two-way coupling.
Well, if there are emergent properties and you're coupling to get that emergent property, we don't know whether the emulator will capture that or not. We're working on it.
Okay. So given that we're into coffee break now, I think this is the point where we can carry these conversations on over tea and coffee. So we will come back at 11:30, please, then, for the next session. Thank you to our speakers.